Okay, buddy, a little recap of the lesson. I'm on page 489. We're still talking about absolute values, but this time we're talking about absolute values with inequalities. So we know that from the baseball example from the day before, that the weight of our baseball has to be 145.045 ounces. But then there can be a variation because in a factory, you can never make it exact. So the variation is about 3.295. We allow that much of a change. Anything within that range is good. So we see that all of these values are acceptable baseball. So we set up an inequality. We knew that if we were able to take 145 and add the 3.295, that's our upper limit. So we can take a baseball this big. If we were to take our 3.295 and subtract it from our baseball, our lower limit would be 141.75. So this is the range of acceptable baseballs from the lowest, 141.75, to the highest, 148.34. So, yeah, 147 would be fine. That would fit within that limit. 140.8, nope, that's too small. 148.34 is exactly at our upper limit, and 141.75 is exactly at our lower limit. So then, okay, well, let's see if we can set this up. So then we turn the page and we say, well, if we were to graph the acceptable on a number line, our acceptables from the 141.75 all the way up to my biggest, which is my 148.34. So we wrote that as an inequality. We can write it as an inequality equation, and then we can solve it, okay? But then we say, well, what about things outside of this region? Those are the baseballs that we have to throw away. So Raymond has a job of disposing all the baseballs that are not within the acceptable weight limits. So he is going to write an absolute value inequality statement. This is going to look like this. He's got the baseball weight minus the 141.75 has to be greater than. If it's greater than 3.295, it's not acceptable. And also less than, and that's where we talk about two different equations. So we graphed it. Anything bigger than 148.34, we throw away. Anything less than 141.75, we throw away. So how do we get this less than? Well, we know that we have two equations. We solve it. That will have a positive and we have the negative. When we have the negative, we turn the sign. We learned that when we did inequalities, okay? So two equations, again, when we solve it, we do the negative, we turn the inequality sign, so it does become less than, okay? Okay, so then we looked at another equation, another problem that exemplifies the same thing. Now we're talking about not weight, but the diameter. How big is the ball? So acceptable diameter is 7.7 centimeters, but you can have a variation of 1.27. So we said anything within this region is acceptable. Okay, so then we set up an inequality of our acceptable weight, which is 7.47, has to be less than or equal to 0.75 as far as the diameter. And then again, we solved it with two equations. We're really careful though when we made the negative part, so we've got the absolute value equals to the 0.75, and the absolute value then is going to be equal to the negative, but when it becomes a negative, we have to then turn the inequality sign, okay? We solve both, and we're able to find the upper limit, 8.25, and the lower limit, 6.72, and then we shade everything in between. These are the acceptable limits of the baseball. And then we did some problems, okay? So the problems we did, first of all, we took number one, and again we talked about two equations. So here's my first equation, x plus 3 is less than 4, and x plus 3 is greater than or equal to negative 4. So we turn the inequality. So we make the negative, we turn the inequality sign, okay? We solve both, and we got x is less than 1 and x is greater than negative 7. We shaded everything in between. No equal sign, so open circle. We took this equation, we turned around, made it look easier if we just turned around. So we took 2x plus minus 4 greater than 6, and then when we made it negative, we turned the inequality sign and we solved both. We got x is greater than 5 and x is less than or equal to negative 1, and we shaded both those. Set notation, I like set notation, it's just a better way to look at it, okay? So it's the same thing. Then we looked at a problem like this, and we had some extra numbers. So before you do a lot, let's get rid of the 2. Don't do anything yet, just get rid of the 2. Go minus 2, okay? Then we do our two equations, okay? We go negative 5x plus 8 less than 23, and negative 5x plus 8 has to be, turn the sign because we make it negative. Okay, we made it negative, so we turn the sign. We solve both, but in this case, tricky, 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 we have to turn the sign again because we divided by a negative again, so turn the sign again. Oh, tricky, tricky, tricky. When I divide by the negative again, I turn the sign again, so we turned it twice. So we wind up with x is greater than negative 3 and x is less than 6.2, okay? D is a trick question because anything that goes in always comes out positive, Anything that goes in comes out positive, and any positive number will always be greater than negative 1, so we say everything, any possible number. It's a little bit of a trick question. And then on the last one, we notice that, again, anything comes in as a positive number has to come out a positive number. Positive numbers will never be less than negative 1, so never no solution, so you don't shade anything. Okay, that's what I had, and the homework I had was page 495 and 496. We also did a couple of math ideas. So if you have questions, come see me.